Good morning. I am Professor Avijit Mandal and welcome you all to our course Radiation Oncology Physics. And this is third week. We are exclusively discussing the various kind of radiation generators which are used in radiation oncology for treatment of cancer patients. And today we are going to deliver the lecture number 15. And today we are going to discuss the different other kind of machines or radiation generators which are used for treatment of cancer patients. In this week we have already discussed various equipment used for imaging, various equipment used for simulation, various therapeutic equipments which are used for external beam radiation therapy, and in this series we are going to discuss the different kind of equipments. They are betatron, microtron and cyclotron. So learning objective of our today's lecture is we will discuss the functioning and principle and working of the betatron, the microtron and the equipment cyclotron. Now betatron used in radiotherapy in early 1950s. It is introduced before the linear accelerator, and betatron is an equipment which is also able to produce wide range of electron energies, wide range of photon energies, and energies ranges from 4 mega electron volt to 40 mega electron volt. So in principle there is no problem with the betatron, and we will discuss about the principle and what are the limitations of betatron in the following slides. Now if we consider the principle or physics behind the operation of betatron, this betatron operated based on the principle that electrons are in a changing magnetic field. They experience the acceleration and in a circular orbit, and this is the principle or physics behind the operation, basic physics behind the operations. So in principle, in a changing magnetic field, electron experience acceleration in circular orbits. Now about accelerating tube used in betatron, it is a hollow donut shaped tube. This is hollow tube, and they are actually highly vacuumed, means they are highly evacuated, and there is nothing within this tube. And these donut shaped accelerated tube placed between the poles of an alternating magnets, and a pulse of electron, and we have in this schematic diagram you can see we have a filament which produce the electron, and this is the circular path of the electron, and this is injector of the, and this is deflector, and here we have a target. So a pulse of electron is originated from this filament. This is the filament. They introduced into this injector into the donut cavity, and this is actually injector purpose to introduce the electron pulse of electron to the donut cavities. When alternating, and when it is injected, when the alternating current cycle begins. So this is the introduction part or injection part of electron, where they are originated from the filament and they introduce into the donut cavity by the injector, and when they are injected in the donut cavities, when the alternating current cycle begins. Now this electron experiences acceleration as magnetic field increases. So they spin with increasing velocity around this tube, hollow tube. They, in the first quarter of the cycle, they actually revolved several thousand times. So in the first quarter of cycles, they are they rotated several thousand times, and they achieved a desired energy and after achieving desired energy, they made spiral out by this deflector. They made spiral out by this deflector, and after this, if we want to use only the electron beam, there is no need of target. But if you want to achieve the if you want to produce the X-ray beam, we need to hit this electron stream, high energetic electron stream, into the target. So this is the basic operations behind of Betatron. So in Betatron, by principle, in a changing magnetic field, electron experiences acceleration in a circular orbit, and accelerating tubes, they are hollow donut shaped and they are highly vacuum, and they place between the poles of an alternating magnet. Now pulse of electrons originated from the filament and they introduced into the donut cavity by an injector. They introduced by this injector, this is the injector, and when they injected, when the alternating current cycle begins. So these electron pulse or electrons experience the accelerations as the magnetic field rises, and they spin around this hollow cavity. They spin around this hollow cavity, and in the first quarter of cycles, they actually completed several thousands of rotations and they achieved the desired energy. And after achieving the desired energy, the energy which we want to use for treatment of cancer patients or want to use for any other purpose, they made spiral out. They made spiral out from this rotational path, and they if we want to use the electron only, so it will coming through, and if we want to produce X-ray beam, we need to hit this high energy electron into this target, so we can get the X-ray radiation. If we compare the linear accelerator versus Betatron, Betatron has some limitations, that Betatron are low current equipment than linear accelerator. So X-ray dose rate, field size capabilities are less effective than LINAC. Even they are less effective, in some cases they are less effective than even cobalt also, as per the X-ray dose rate and field size capability, because in Betatron we are not able to treat very small target volume. So and this is the problem in only X-ray mode, but electron mode is adequate as compared to the LINAC, and it requires a very high degree of flattening filter because of the type of Bremsstrahlung process happened in the Betatron target and the energetic electron. They requires high degree of flattening filters, and this is made the equipment very bulky, and these are the limitations which cause to not so promising equipment for the treatment of cancer patients or for the treatment in the radiation oncology field. So Betatrons have the problems with only low current equipment, and the dose rate and field size capability is less effective than LINAC, and even they are less effective than cobalt also. But you should understand that electron therapy mode is adequate as compared to the linear accelerator. Now coming to the a special equipment that is known as microtron, and microtron actually combined the two kind of equipment. One is linear accelerator and another is cyclotron. So you can say microtron is the equipment which combines the design of linear accelerator and the design of cyclotron. Now electrons accelerated when they experience a oscillating magnetic field. One or more microwave cavities, they may be klastron or they may be magnetron. In last class, while discussing the linear accelerator, we have discussed about the klastron and magnetron. They are microwave cavities, microwave generators, or you know that magnetron is microwave generators and klastron is a microwave amplifiers. So in microtron, there may be one or more microwave cavities are used. Now these electrons received higher and higher energy after each passing of the microwave cavity. We will discuss and the schematic diagram later. and orbit increasing radius in the magnetic fields. These orbit actually are increasing in radius in the magnetic field after passing each of the microwave cavity. The cavity voltage, the frequency, the magnetic field are so adjusted that electrons arrived in correct phases. There must be correct phasing of electron in such a way that they can receive higher and higher energy after each passing of microwave cavity. Now, the extraction of electrons process have performed by using a narrow deflection tube. These narrow deflection tubes are made up of steel. They are actually screens the magnetic field, and the high energy electron beam may strike to the target if you want to get the X radiations. So, in short, microtron is a combination of linear accelerator and cyclotron, and electron gets accelerated while experience a oscillating magnetic fields and passing of one or more microwave cavities. These microwave cavities may be klystron or may be magnetron, and they received higher and higher energy after each passing of microwave cavity. Now, this orbit actually defines by the increasing radius in the magnetic field, and the cavity voltage is an important parameter. The frequency and the frequency of the alternating field and the magnetic field are adjusted such that the electrons arrived in correct phases in each passing of the microwave cavity. And the extraction, how we extract this electron high energy when we get the desired energy, we use a narrow deflection tube. And this is made up of steel. This steel tube is used to screen the magnetic field, and high energy electron beam are made strikes to the target when we want to get X radiation. Now, here is two type of design available for microtron facility, microtron installation. First one is racetrack design, and where there is a single microwave cavity or waveguide is used, and this actually needs very bulky structure, and this is the limitations of this racetrack design and bulky structure to accommodate the large magnetic gap and large magnetic diameter, because this diameter we need to have a bulky dimension or bulky structure of units. So, this design is not popular in working or radiation oncology field, because we have limitations of spaces and in radiation oncology department. So, this design is not popular. Now, these design problems or limitations are removed by this second design, where they use the multiple microwave cavities as a linear accelerator cavities, and there is a two magnets are used, and these electron branches, these are electron branches, and this is actually extraction magnet by which we can extract the beam after achieving the desired energy, and this beam may be made strike to the target. So, in this design you can see that we have electron gun, and this electron gun there is bending magnets, and these are actually bending magnets, and these bending magnets move the electron beam to the inject to the linear accelerator multiple microwave cavity, and they come to they are experience alternating field of magnetic field, and after each passing these are such that they are the cavity voltage and the magnetic field and alternating field frequencies are adjusted so that they come in proper phases for after passing after each passing of the cavity. So, this removes the constraint by using a standing wave and using of multiple cavities. So, after that we will get a smaller size or lesser dimension microtron unit, And advantages of microtron over linear accelerator is its simplicity, the energy is easy energy selection mode, the small beam energy spread, and easy and simple beam transport system, smaller sized machine, as we have already discussed. So these are the advantages of microtron over linear accelerator, and this is simplicity, easy energy selection, small beam energy spread, easy and simple beam transport system, and smaller size machine. Now our last equipment is cyclotron, and this is the equipment, very important equipment for they are used for multiple purpose. They actually used in as a charge particle accelerator, and they are widely used for nuclear physics research. This cyclotron is normally used for nuclear physics research, but in radiation oncology we use the particle beam, as we use the electron beam, as we use the photon beam and gamma radiation. We also use particle therapy, different kinds of particles such as protons, heavy charge particles like pions, and we also use the neutrons. And these heavy charge particles means protons and pions, and the neutral particles such as neutrons are also produced by the cyclotron equipment. So from the cyclotron we get the high energy protons, we get other heavy charge particles, and we also get the high energy neutrons, and these are used for radiation oncology. We know that particle therapy has a distinct advantages of Bragg-Gray cavity. This is already discussed during interaction of radiation with matter, where we discuss the interaction of heavy charge particles with matter. You must understand that there was a, if we plot a curve, it will looks like, means the charge particle delivers almost most of the energy at the end of its range. So the superficial structures placed before the target volume, this is actually known as Bragg's peak, and this is the Bragg's peak, and this is the distinct advantages of particle therapy. And cyclotron is the equipment which give us the heavy charge particles like protons, pions, and also give us the neutrons. You also know that we have also discussed the interaction of neutrons with matter during our first or second classes. Now here is the cyclotron. Now what is the structure? In structure or design, structural design, you can see there is a short metallic cylinder. There is a short metallic cylinder which is divided into two sections. Here one section and here second one. So this short metallic cylinder is divided into two sections, and they are known as D. This cavity actually highly evacuated, and this D is placed between the poles of direct current magnet. This direct current magnet produce constant magnetic field. An alternating potential is applied between the Ds. Between these there is an alternating potential is applied. This is the alternating potential. This is high voltage, high frequency oscillating potential. So in structural design there is a short metallic cylinder which is divided into two sections Ds, and these two sections are highly evacuated, and these two Ds are placed. This is not shown in the figure actually, and this is placed between the direct current magnet, and with this direct current magnet producing constant magnetic field. And an alternating potential, this is the alternating potential, is placed between the Ds, the two Ds, and in this design we have an ion source. Now if we discuss operation of the cyclotron, you can see here you have a ion source placed here, which injects the proton or deuteron. This is the ion source. This is the ion source which produced or inject the charged particles, that may be protons or deuterons. And these charged particles, positively charged particles, injected into the chamber. This is the injection process. They injected into the chamber, and under the action of magnetic field, they start rotation, and the frequency of the alternating field, these we have already mentioned that there is a frequency, there is a alternating field applied between two Ds. The frequency of this alternating field is so adjusted that as particle passes each D to other, the polarity changes and gain acceleration. Now, if electron is placed here, then it is positively charged particle is placed here, and we have a negatively charged D. Now when this electron comes out of this D, the second D is again changes its polarity to negative, so it attracted towards this D and it gains the accelerations. So each passes between the D's, the particle energy increased and radius of the orbit also increased for each passes, and making many revolutions, the energy reached up to 30 mega electron volt. And after this we use a deflector system which eject the electron beam and remove the electron beam from the orbit, and it may be hit the target. Sometimes if we need only particles, there is no need of target, but if we need neutrons, we need a appropriate target. We will discuss later on. We need a appropriate target to get the neutron beams. So in short, the cyclotron operations, they are positively, we have a ion source which inject the positively charged particle, that may be protons or may be neutrons, injected into the chamber, and these charged particles under action of magnetic field rotates circular orbits, and the frequency of the alternating field is so adjusted such that as particle passes one D to other, the polarity changes and gain accelerations, and each passes between D's, the particle energy increase. That means the increase of radius of the rotation, and after making many revolutions within this cavity, the energy reached up to 30 mega electron volt. And if we want only the positively charged particle, we will just remove this particle beam from this cyclotron, and we can use for the treatment or for any other purpose. But if we want to get the neutron beams, the deuterons are accelerated up to high energy 15 to 50 mega electron volt, and they strikes a low atomic number material target such as beryllium, and neutron are produced by the phenomenon, this is known as striping phenomenon of the nuclear physics. Now here we have used the low atomic number material. Now you may recall that during the X-ray production we use high atomic number material as a target, but here we are using a low atomic number material as a target, and in X-ray production we use the high Z material, but in neutron production we use the low Z material such as beryllium. So by these neutrons are produced by the phenomenon of striping phenomenon. This is known as striping phenomenon, where this is the deuteron particle 1H2, and plus they are not actually captured by the beryllium nucleus for beryllium 9. The protons of the deuteron stripped off, and the residual neutron is traveled with high speed, and this is how we get the neutron, because this is a uncharged particle, and we get the high speed neutrons for treatment or for any other purpose. So neutron productions by cyclotron is also very important. So by cyclotron we can use for acceleration of heavy charged particle, positively charged particles, or we can get the neutrons from this cyclotron. Now we have already mentioned that cyclotrons are used in nuclear physics research. They are widely used throughout the globe, and in radiation oncology we use particle therapy for neutron therapy, for proton therapy, or for any other heavy charge, positively charged particle therapy. And cyclotron also used for the production of artificial radioactive materials. They are commonly used in nuclear medicine department, where any institute can in-house produce the radioactive material. They are short-lived radioactive materials which are used for diagnostic or therapeutic purpose. So this is all from my side. This is the end of our third week, where we have discussed the various kind of radiation generator used in radiation oncology department. Thank you.